media posted a link to a series of videos titled The Ultimate Monad Tutorial. And since monads were a topic that I was personally struggling with for a rather long time, I decided to watch it. What I saw was roughly the same narrative as the one that I have previously experienced in countless other monad tutorials that I have read and watched, and which I haven't found very helpful for understanding monads. The first thing that I find misleading is that they try to derive the notion of monads by abstracting a common pattern from a set of fairly complex examples that no one actually cares about, which is not how monads were historically developed. The second thing is that they almost completely ignore the main reason why programmers get interested in the notion of monads in the first place, namely because they want to print "Hello World" in Haskell. I personally think that the easiest way of understanding monads leads through the so-called point-free style of programming. This style of programming is sometimes called pointless style, and this name actually has a point. But let's have a look at it anyway. Suppose that you want to have a function which says whether the length of its parameter, a textual string, is even. You would normally define it in JavaScript-like notation as function is length even of string, return is even of length of string. We could also write it down using a more Haskell-like notation. Is length even of string is equal to is even of length of string. The same definition expressed in point-free style would look like this. Function composition of f and g defined as return function of x, which in turn is defined as return f of g of x. In Haskell, the composition operator is usually expressed using a dot or a small circle and is placed between its arguments. So f composed with g of x is defined as f of g of x, and we can use it to define is length even as is even composed with length. It is now instructive to look at the type signatures of the functions involved. The length function takes a list or a string and returns an integer. Likewise, the isEven function takes an integer and returns a boolean, true or false. The returning function isLengthEven takes a string and returns a boolean. So, what could we say about the type signature of the composition function? In our case, as its first argument, it takes a function from integer to boolean, and as its second argument, it takes a function from string to integer. It produces a new function from string to boolean. It may seem a bit twisted at first, but in general, we can say that the input type of the first argument, let's call it b, must match the output type of the second argument. The input type of the second argument, let's call it a, will become the input type of the result. And the output type of the first argument, let's call it c, will become the output type of the result. This may seem a little bit awkward at first, but if we had flipped the order of arguments in the composition operator, defining f backwardly composed with g of x as g of f of x, then its type signature becomes a very natural and very pleasant to read. It is something that takes a function from a to b and a function from b to c and returns a function from a to c. So it sort of swallows the middle type. One thing that mathematicians like to point out is that if we define the so-called identity function, that is a function that simply returns its argument, then it is a neutral element of function composition, which means that for any function, f composed with identity is the same as identity composed with f, which is the same as f. So it doesn't affect our result. And this is interesting because in this regard, the identity function behaves for the function composition in the same way as a 0 behaves for addition and 1 behaves for multiplication. Another thing that function composition has in common with addition and multiplication is that it is associative, which maybe isn't something that we're going to particularly focus on, but it might be interesting to some viewers to know that mathematicians call such algebraic structures monoids or semi-groups with unit. Okay, let's now recall the type signature of the function composition operator. The type signature of the identity function is rather straightforward. It always returns a thing of the same time as it receives. Let's think for a moment if we could somehow generalize these operations, or whether we could construct, a more general variant of function composition, or, I don't know, come up with a composition operator that would also do something extra. If you've programmed in languages such as C#, Java, or TypeScript, you may have encountered the notion of generic classes or parameterized types. For example, the type list can be parameterized with some other type, so that it can construct lists of strings, lists of numbers, lists of booleans, and so forth. And this is how we can arrive at the notion of monads. Suppose that M is some generic type, so it accepts some other type as its parameter. We can define the function composition operator so that instead of returning a value of a given type, it returns a generic type parameterized with that type. And we can adjust the type signature of the identity function to make it usable with this generalized composition. And if you feel at this point that the above generalization is awkward, you are completely right. I don't think there's a lot of people who would have come up with something like this because it doesn't seem to solve any practical issues. But at least we have a first approximation of the answer to the question, what is a monad? So, hear me out. A monad is a weird generalization of the function composition operator. Now, I'm sure that there are some angry nerds out there who, hearing this definition, would start waving their fists and shouting, "Oh no, this is not true! A monad is a generic type plus a weird generalization of the function composition operator and an adequate generalization of the identity function." And indeed, a formal definition of a monad is that it is a triple. Once we have this definition, we could try to substantiate with some example. Probably the simplest one that comes to mind is a logging facility. Suppose that we have the following generic class. As you can see, it has two fields, a field of generic type t called value and another field of type string called log. The extended composition operator for functions returning elements of that class could look like this. F composed for with log with g of a is defined. So first we take g and we apply it to a, to this argument. And in this way we return an object of type with log that we call b. We extract the value field from this object and we pass it to the function f, obtaining a new object of type with log that we call c. And then we return a new object of type with log whose value field is the same as that of the c's object and whose log value is a concatenation of two logs, of log from b and log from c. And the extended identity function, which is defined by our definition of monad, would just return a value with an empty string as its log. You can easily find many other examples. In particular, a lot of monad tutorials like to present the so-called maybe or optional type and its composition operator. So now that we know what a monad is, we can move on to the other topic, namely, what does it have to do with the input and output operations in Haskell? But maybe we should start with the question, why are the input and output operations problematic in Haskell? So you may have heard that Haskell is a lazy language. In practical terms, it means that it tries to postpone evaluation of its expressions to the moment that the implementation finds most convenient. Or, in other words, that it is very hard for programmers to predict when a certain expression is going to be evaluated. And this order is also extremely brittle, so it's really hard to rely on it. So consider the following expression. Read number times 3 plus 2 times read number. Suppose that when we run it, it asks us to provide some input. And then we type 1 and enter, 0 and enter. What will be the value of this expression? In order to answer that, not only in Haskell but in any language, we would need to make some assumptions, such as suppose that the expressions are evaluated from left to right. And in many languages, this order is actually unspecified. But in Haskell, the situation is even worse. It doesn't even assume that read number will be evaluated more than once. So the value of the whole expression could be 3, but it could also be 2, 5, 0, or something completely different, because read number could technically occur somewhere else in the program. Or, I don't know, the program would have no reason to evaluate this expression. Most languages specify that function arguments are evaluated before evaluating the function itself. So by assuming that let x be equal e in body is a syntactic sugar for invocation of the anonymous function of argument x which returns body and is called with the argument e, we could rewrite the program as let a be the value returned by read number in let b be the value returned by read number in a times 2 plus 3 times b. But in Haskell, this won't work because the arguments can be evaluated even after calling the function. However, we could enforce the order of evaluation by introducing an explicit dependency between two invocations of read number. So now, let the pair AW1 be the value of read number of W0 in. Let the pair BW2 be the value of read number of W1 in A times 2 plus 3 times B. So in this solution, read number accepts an additional parameter and returns an additional value. If we want to obtain the value b, we must have w1, and in order to get w1, we must evaluate read number of w0. Moreover, if we wanted our operation to be composable using the same scheme, we would also have to return the token w2 along with our long-desired return value. The values w0, w1, and w2 belong to a special type that the designers of Haskell called real world. But their essential property is that the compiler knows nothing about them, so that it cannot establish the value of w1 without actually evaluating the expression number of w0. Haskell also defines a type alias for a function that takes a real-world value and returns a pair consisting of value of some generic type A and another value of type real-world as I/O of A. If you want to find out more, I recommend the article titled I/O Inside that you can find on the Haskell wiki. What I would like to point out is that we have covered a large portion of the design of Haskell's I/O system without ever mentioning the word monad. And indeed, the presented idea has essentially nothing to do with monads. However, if we look closer at the practical aspects of this approach to interfacing with the real world, we can immediately see some problems with it. More specifically, we are burdened with the necessity of passing additional parameters to our functions. But we also need to keep track of whether we pass the right parameters. What would happen if, instead of passing the value w1 to the second invocation of read number, we would have mistakenly passed w0? Another issue is that with each input-output operation, the indentation level of our code increases, which is just annoying. So when it comes to the first two problems, we could define the following pair of functions. Pass value to continuation, which returns a function of argument w0, which applies the value function to the w0 argument, obtaining the pair result and w1, and then calls continuation with result and w1. And return value is defined to return a function of argument world, which returns a pair consisting of the argument passed to the return function and the world passed to the resulting function. This would allow us to sweep the extra parameter passing under the rug of function invocation, making our definition look like this. Pass read number to function of A, which passes read number to function of B, which invokes return A times 2 plus 3 times B. It may not be immediately obvious that this expression is equivalent to our original program, and substituting the occurrences of pass and return with their definition bodies using a pen and a piece of paper is a good exercise. But I have also prepared a primitive animation which presents this process, so you can just try to believe your own eyes. Okay, so this seems to solve the problem of parameter passing, but what about the increased level of indentation? Obviously, we could just remove all the preceding white space and call it a day, but a program written in that way looks a bit awkward, and the level of nesting of parentheses still increases. The problem isn't unique to I/O operations in Haskell. As a matter of fact, it is so ubiquitous in programming that it even has its name, and it is called the Pyramid of Doom, because the white space near the left edge of the code start forming a triangular shape. But this sort of problem can be solved by introducing syntactic sugar. So we can imagine that our language provides us with special syntax so that do result left arrow action actions dot 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 is transformed to pass action function of result do actions dot dot dot. So we recursively apply this notation during the transformation. And this allows us to express our program as bind the result of calling read number to A, then bind the result of calling read number to B, and return A times 2 plus 3 times B. And this pretty much resembles programs written in traditional imperative style. Let's now have a closer look at the types of functions that we have defined. The return function takes a value of any type A and returns a function that takes real world and returns a tuple consisting of the value of type A and a value of type real world. But as we can recall, the result type of the return function can be referred to as I/O of A, because this is the type alias that Haskell's I/O system introduces. The type of this function should remind us of the type of the identity function from the definition of monad. The type of the pass function is a bit more tricky. We can see that the value argument receives some argument and returns a pair, so it must be a function. But the type of this function can also be abbreviated to I/O of A. The continuation argument is capable of receiving the value of type A, and it produces something that is capable of being applied to the value W1 of the type real world. If we recall our requirement that we wish to be able to further compose the value returned from pass by placing it in another call to pass, then we must conclude that this value must be a tuple consisting of some type B and a value of type real world. So we can conclude that the pass function is something that takes an element of type I/O of A and returns a function which takes something of type A and returns something of I/O of B. The result of using that function must be something of type I/O of B. This isn't quite the type signature that we've introduced with our definition of a monad. But notice that once we have the pass function, we could define the monadic composition operator in the following way. F monadically composed with g of x is equal to pass the result of g of x to f. Note that if we assume that x is of any type A, then g must be a function from A to I/O of some type B. Moreover, f being the second argument to pass must be a function that takes some type B and returns I/O of some type C. So the type of our monadic composition operator is the following. So it takes a function from B to I/O of C and a function from A to I/O of B and returns a function from A to I/O of C, which is exactly the type of monadic composition. Okay, if you don't enjoy this type level mumbo jumbo, that's completely fine. The key takeaway is that the pass and return functions that we have defined here satisfy our earlier definition of monad. But of course, this alone isn't particularly useful. What is more interesting is that the type system in Haskell is powerful enough to allow to define pairs of functions, pass and return, for various different generic types. This makes the do syntax applicable not only to functions operating on the generic type I/O, but also to any generic type for which we define pass and return, thereby allowing us to solve the pyramid of doom problem in various different contexts, like, for example, asynchronous programming. And by the way, Haskell doesn't use the name pass, but instead it uses an operator greater than equals, which is traditionally pronounced as bind, because why not? So this leads us to another view of monads. A monad is an interface that allows us to use the do syntax in Haskell, which in turn allows us to deal effectively with the problem of systematically increasing indentation of our code. To summarize, we have seen two takes on monads: that it is an awkward generalization of function composition operator, or, more practically, that it is an interface that allows us to use the do syntax, which solves the problem of increasing level of code indentation. I hope that you found this explanation helpful, but even if you did, please do not subscribe to my channel. I use it for posting random stuff, mainly for sharing clips from the ongoing development of the visual editor for the scheme programming language that I work on in my spare time. But It's very possible that I will start posting videos of myself playing guitar and singing my favorite songs, and it's very unlikely that you want to be notified about this. If you really need to stalk me on the internet, you can follow my Mastodon account, which can be found at functional.cafe/@paniczgodek. I also occasionally write answers on the Quora website. So, thank you for your attention, and I really hope that you're going to live your life fully and happily.